Antineutrinos can fly through a reactor wall, a mountain, and most of Earth without stopping. That makes them almost impossible to catch. It also makes them almost impossible to hide. Researchers have calculated that these ghost particles could expose a fusion facility being used to produce plutonium. The suspicious material might stay behind concrete and steel. Its antineutrinos would not. So how can a particle that barely touches anything reveal a secret inside a locked building? Start with an ordinary fusion machine. It squeezes light atomic nuclei together. In the leading design, deuterium joins tritium. The collision makes helium, energy, and a very fast neutron. That neutron has no electric charge, so it can escape the magnetic field holding the fusion fuel. Around the machine sits a thick blanket built to catch it. In a future power plant, this blanket may contain lithium. Neutrons hitting the lithium can make fresh tritium, replacing fusion fuel that was burned. But the same neutron supply creates a security problem. Someone could place uranium-238 in or near that blanket. Uranium-238 is common compared with the rarer uranium used directly in weapons. When it captures a neutron, it becomes uranium-239. That new atom is unstable. It changes into neptunium-239. Then it changes again into plutonium-239. Plutonium-239 can release enormous energy through fission. Producing it does not automatically create a weapon. The material must still be separated, processed, and engineered. But covert production would be a serious warning sign. Inspectors could look for uranium. They could inspect the blanket. They could track materials entering and leaving the site, unless access is blocked. Concrete can hide equipment. Steel containers can hide samples. Records can be false. But the two radioactive changes on the road to plutonium release something no wall can hold back. Each change emits an electron and an antineutrino. The electron stops nearby. The antineutrino shoots away. Billions upon billions can cross solid material as if it were empty space. That sounds like perfect camouflage. Yet every newly produced plutonium atom is tied to a predictable chain of changes. The escaping particles become a kind of receipt. Fusion itself is important here. The main deuterium-tritium reaction does not produce this same antineutrino trail. Its headline products are helium and a neutron. Add uranium breeding, and a new ghostly signal appears. But reading that receipt is brutally hard. A camera catches light because photons strike its sensor. Antineutrinos almost never strike anything. A huge number can pass through a detector without leaving one useful mark. Researchers therefore studied an interaction called coherent elastic neutrino nucleus scattering. The name is long. The event is tiny. An antineutrino taps an entire atomic nucleus. The nucleus recoils by an absurdly small amount, like a bowling ball moving after a speck of dust hits it. That tap can be measured only by extremely sensitive detectors. The detector must separate it from natural radioactivity, cosmic particles, vibrations, and electronic noise. Shielding can block many of those imposters. It cannot block the antineutrinos, which arrive straight through the shield. That is the central contradiction. The shield removes what is easy to stop. The evidence survives because it is hard to stop. The researchers modeled the antineutrino glow expected when fusion neutrons convert uranium toward plutonium. They then asked whether detectors outside the dangerous machinery could distinguish that glow from background noise. Their result was not a magic plutonium alarm. It was a calculated path to monitoring. With suitable low-threshold detectors, enough exposure time, and a location close enough to the facility, the extra signal could reveal that breeding was happening. The count rate would also rise and fall with activity. Stop the neutron source, and production stops. Restart it, and the signal returns after the short-lived atoms in the chain build up again. That changing pattern can help separate a real process from steady background noise. There are still hard limits. Antineutrino signals fade quickly with distance because the particles spread in every direction. Nearby nuclear reactors can add noise. Detector sensitivity must improve. Inspectors would need accurate models of the facility and careful statistics. And the signal alone would not prove that someone had built a bomb. It could flag suspicious plutonium production. Investigators would still need inspections and other evidence. That distinction matters. This is a proposed safeguard, not a finished global surveillance system. Yet fusion safeguards need to be designed before large fusion plants become common. A powerful neutron source can serve clean energy research. The same neutrons can also transform hidden material. Waiting until facilities are everywhere would make monitoring much harder to add. So return to the wall around our secret reactor. It can stop people. It can stop cameras. It can stop radiation that normally gives nuclear material away. But it cannot stop the quietest witness. The particle that almost never interacts can carry evidence out of the building precisely because nothing inside can catch it. Antineutrinos are difficult to detect for the same reason they are difficult to conceal.